So question 9 is a question we probably call an empirical formula question. We're trying to work out the formula of an unknown compound. So in this case, we've got titanium here, and we're trying to work out what formula titanium oxide is. The way we do that is we heat it in a crucible. That's going to allow oxygen to react with the titanium. It's going to get heavier, and we're trying to see how much it's got heavier to work out how much oxygen's been added, and that allows us to get the formula at the end. So, information we've got the mass of the crucible at the start, the mass once we add some titanium to it, and the mass after it's been heated, and it's got heavier there because now titanium oxide. First little theory question, why is it necessary to lift the crucible lid during heating? Again, that's not too complicated. We're trying to react this titanium with oxygen. If we keep the lid on, which is there to keep heat in, the oxygen's going to run out. So we need to lift the lid off occasionally to get a little more oxygen in. So the answer there so it's to allow air to enter the crucible. The main bulk question is a calculation, also say it's 6 marks. We have to use the experimental results to determine the empirical formula for the oxide of titanium. So if you remember, the key kind of bit working out for this type of question is to work out the mole ratio of titanium to oxygen, because those are the two elements in this compound. So if I kind of lay it out like this, titanium with respect to oxygen. Now I haven't got moles at the start, all I've got is masses, and even with the masses there's a little bit of working out to do. First thing I need to do is work out how much titanium is there. So the mass of titanium is the mass of the crucible with titanium minus the mass of the crucible by itself. So if I take that 18.34 away from the 19.36, I'm basically subtracting the weight of the crucible from the titanium. So if I do it off the side here, 19.36 minus 18.34 gives me mass titanium of 1.02 grams. So that goes in there. Mass of the oxygen, so once I heated it and reacted with oxygen, it got heavier. So we got from 19.36 up to 20.04. So that increase in mass is from the oxygen. So if I take 20.04 minus 19.36, subtract them, I'm going to get 0.680 grams. So that is the mass or the ratio in terms of masses, but I need to get it in terms of moles for this question to work. So number of moles is mass over mR. So for titanium, it's going to be 1.02 over, it tells me here titanium is 48, and that is just going to be 0.02125. For oxygen, 0.680. I have to be careful here. It is just oxygen, it's not diatomic because it's in the compound. So just use 16 rather than 32 for twice. And that gets me 0.0425. So again, you might spot the ratio just by looking at it, but if you're in doubt, remember always divide by the smaller bit of the ratio, which is this one, 0.02. If you divide them both by that number, you actually get a 1 to 2 ratio. And that means for every 1 titanium, there are 2 oxygens, therefore the formula becomes TiO2, which is your answer. Okay. Next question, one marker, just about empirical formula again. No calculation here, it's just saying if you understand what empirical formula actually means. So you got this long formula here, C21H22N2O2. So if you think about the questions trying to see, can you get that into a simpler whole number ratio by cancelling down? It's almost a bit of a trick question here. You actually can't. The problem is that C21, thinking maths wise, you can divide 21 by numbers, you divide by 7, divide by 3. That wouldn't work for the other ones. To get them to whole numbers, you only really divide by 2 for all these numbers, which doesn't work for this. So basically the empirical formula is that, the way it's written already. You can't actually get any more cancelled down than that. So the empirical formula is the same as the molecular formula for strychnine. Question 11, about an empirical formula calculation. It's a little bit different, involving percentages. So it's giving you all the different elements in a compound called urea, carbon, hydrogen, nitrogen, oxygen. It's giving you percentages of those elements in the mass of the compound, and then it's asking you to work out what the empirical formula is. So remember, with percentages, you just treat them like masses, because if you had 100 grams of this compound, you'd have 20% of 100 grams, which is 20 grams, 6.6 grams, 46.67 grams, etc. So percentages you treat like masses in grams, because your matching is out of 100 grams. So if I lay out my ratios, again, same kind of working out with empirical formula, just trying to get the mole ratios of all the elements and then trying to get the simplest whole number for that. So those are my 4 elements. In terms of percentages, I've got 20% or 20 grams for carbon, 6.66 for hydrogen, 46.67 for nitrogen, and 26.67 for oxygen. To get them into moles, I have to divide them by their atomic masses. Now, handily, they give them for you in the question. Carbon is 12, hydrogen is 1, nitrogen is 14, and oxygen is 16. So remember, what I'm doing here is just doing moles equals mass over MR, or mass over RFM. Sorry, I should explain, I'm using a wee n there, that's like a wee kind of shorthand for moles. So moles equals that fraction. Plug into my calculator, get these numbers: 1.66 to 6.66 to 3.33 to 1.66. Again, if you're very mathematical, you might spot that ratio just by looking at it. If in doubt though, remember, divide by just the smallest number of the set, which is 1.66. If you do that, you get 1 to 4 to 2 to 1. That means the empirical formula is 1 carbon, 4 hydrogens, 2 nitrogens, and 1 oxygen, which gives you CH4N2O. Question 12 is a wee bit different. So we're going on to water crystallization here, where you're trying to see how much water is contained in a compound, a hydrated compound. So explain, give experimental detail, how you determine the mass of water crystallization present in a sample of hydrated calcium chloride. Include any details of any mass measurements you'd make and the equipment you would use. So obviously there's no calculation here, it's just trying to see if you understand the experiment. These questions can be quite tricky, because whilst you might kind of in your head know what's going on with the experiment, it can be quite hard sometimes to put them down in a logical order. So first thing, if you're going to think of the design experiment, it generally involves weighing lots of things and heating them. So essentially what you want to do is weigh a container. Now I would probably say a crucible would be the best thing. So weigh a crucible with the hydrated. So hydrated means you haven't heated it yet, it's just the solid you got to start, with hydrated solid inside it. Next point, heat it. I would probably say as a safety point, you have to cool it down first so you don't immediately pick it up, and weigh. So you're saying if it's got any lighter from heating it on the Bunsen burner. Next thing is kind of to repeat it until it no longer changes. Another way of saying that would be to heat until constant mass. So in other words, you heat it, you measure it, see if it's got any lighter. Heat it again, weigh it, has it got any lighter still. You keep doing that until it stays the same, because that tells you you've removed all the water you can remove from it. So you have to keep going back and forward until it stays a constant mass. Now you have to actually explain any mass measurements and any kind of, it implies you have to know what you do with those results. So once you've got your constant mass, you have to subtract the final mass from the initial mass to find out the mass of water that's been removed. Remember, the question says, how would you determine the mass of water present? So that's explaining how you actually know what's been removed. Any equipment you use, so obviously you can intersperse it throughout, or you can sort of list it at the end. So crucible we won't put. You probably would mention about your heating apparatus as well as your final point. So you need a Bunsen burner for heating. You put a tripod on top of your Bunsen burner. You would use a gauze to hold your crucible or your evaporating dish, whatever you're using. Or your pipe clay triangle would be another option. So all that just gets you 6 marks there. Okay, on to question 13. So this is a water crystallization question. Now it's very similar on your notes, but this is laid out more in a past paper style. It's trying to work out the number of moles of water crystallization in hydrated magnesium sulfate. So it's magnesium sulfate with a few waters attached to it. You're trying to work out how many waters there are. Remember, the basic principle of this question is you want to work out the mass of the magnesium sulfate first, the mass of the water you removed, convert them to moles, and then see the ratio between them to get the number of waters that are there. So, lead you through it though in this question. So first one, explain why the student weighed the crucible and the contents several times during the heating process. Again, it's the idea of making sure you're heating it until the mass doesn't change. So that's called heating to constant mass. Part 2, calculate the mass of water crystallization loss. So they're trying to get you to work out the water first. So with the water, you're trying to see, well, how much lighter has it got from when it had water to when there's no longer any water. So the hydrated magnesium sulfate with the crucible weighed 13.96. The crucible, after you heated it and the mass hadn't changed, has gone down to 13.33 grams. So that's your decrease there. See, these are both the same. You've done the experiment properly. It hasn't got any lighter. So it's that difference there is the water's been lost. So 13.96 minus 13.33 equals 0.63 grams is the amount of water that was lost in that experiment. Part 3, calculate the number of moles of water crystallization loss. This is a 2-mark question, but it's not too much working out to get it. You've already got the mass that was lost. You just have to use moles equals mass over RFM to get the answer. So it's 0.63. The RFM water gets you mark. So H2O you have to know 2 hydrogens, 1 oxygen. So it's 1 plus 1 plus 16 is 18. If you do that, you end up with 0.035 moles. Little exam tip at this point. Generally with CA questions, most of the mole answers you get will be kind of round numbers. If you end up with a big string of like recurring decimal places, it's probably an idea you maybe have done something wrong. I mean, it's not a proper hard and fast rule, but it's maybe the idea you should probably double check your answer. 0.035 exactly seems like a reasonable number for a CA answer there. Calculate the mass of anhydrous magnesium sulfate. Have to be really careful here because it's very easy to pick the wrong masses. The temptation is to use this 13.96, the hydrated magnesium sulfate, and then take away the mass of the crucible. That would give you the mass of the magnesium sulfate with the water still attached to it because it's still hydrated. All you have to work out is what's the mass of the magnesium sulfate that's being dried out minus the mass of the crucible. So it's actually the 13.33 take away this 12.73, not the 13.96. So 13.33, because that's once all the water's been removed, it's now anhydrous. Take away the mass of the crucible, 12.73, equals 0.6 grams exactly. Same kind of step here, you're trying to work out the number of moles of anhydrous magnesium sulfate. Same step again, moles equals mass over RFM. You work out the mass. RFM takes a wee bit working out. It doesn't actually give you the formula of magnesium sulfate, which obviously makes it a trickier question. You have to basically do a wee swap and drop. Magnesium is in group 2. Sulfate is on the back of periodic table, SO4 2-. So swap and drop that, get you MgSO4 because 2 and 2 cancel down. If you add all that up, your RFM becomes 120. 0.6 over 120 gives you 0.005 moles. And again, we kind of common sense check. If it's coming out like a nice roundish number like that, it's probably a good idea you've got the correct answer. So what you've now worked out is the number of moles of water lost. You've also worked out the number of moles of magnesium sulfate you had at the end. Gives you a wee clue of the last part of the question. Using your answers to part 3 and 5, calculate the number of moles of water crystallization contained in 1 mole of hydrated magnesium sulfate. Basically, it's asking you how many waters are attached to each magnesium sulfate. So for 1 mole, how many moles of water? If you look at your ratio, magnesium sulfate to water, you've done all the work on that already. You worked out there's 0.005 moles of magnesium sulfate, and corresponding to that, there's 0.035 moles of water attached to that. Again, I'll be careful here. There is a ratio, you can make it simpler. Divide by the smallest, or just look using your common sense work out. That is actually a 1:7 ratio. 7 5s are 35. But if divided both by the 0.005, I will get 1:7. Therefore, the final answer, I don't need to give the formula because it's just asking the number of moles of water crystallization, which is just 7. It could have asked me the formula. The formula would be MgSO4.7H2O, but that's not the question in this case. Question 14. Again about some tooth whitening agent, hydrated silica. And it starts off with a little definition question. So it says, hydrated silica contains water crystallization. What's meant by that term? Again, that's this wee line out of your notes you have to learn. It's water of crystallization is water chemically bonded into the crystal structure. Part 2, calculate the percentage of water crystallization present in hydrated silica. So that's a percentage calculation which we did right at the start of the booklet. So it's basically of that total mass with 2 waters attached to it, how much of that total comes from the H2Os. So there's 2 parts to that. Have to work out the mass of the whole thing, and that's just a wee bit of calculator work. Silicon's 28, oxygen is 16 times 2. You hopefully know by what now that water has a mass of 18, 1 plus 1 plus 16. 2 of them makes 36. Add that all together becomes 96. The mass that comes from the waters is just this bit, the 2 H2O. 2 18s is just 36. So that 2 numbers there going together, the percentage mass coming from the water is going to be 36 over the total, which is 96, times by 100, gives you a final answer of 37.5%. Final question on this page, hydrated aluminium oxide doesn't give you a number of moles of water. You have to work out the value of N using this information. It's not as tricky as this one because they don't give you a wee complicated table to work out all the different masses. They actually give you the masses at the end just in one bit. So what you've got is hydrated aluminium oxide, 3.12 grams of it. You've heated it to 2.04 grams. So that's the 2 masses they give you. Again, laid out like I did before, I'm trying to get the ratio of aluminium oxide to water. So first of all, I need to work out the masses. Again, I have to be really careful here. The mass of the aluminium oxide by itself is not 3.12 grams, which you might be expecting. The reason is that is for the hydrated aluminium oxide. In other words, the aluminium oxide which still has the water attached to it. I need to get the mass of the aluminium oxide once all the water has been taken away, which is 2.04 grams of it. So 2.04 grams is the mass of the aluminium oxide. The mass of the water is just how much lighter it got, because this 3.12 grams is with water, this 2.04 grams is without water. So to work out the mass of H2O, you need to do 3.12 take away 2.04, which gives me 1.08 grams there. Again, I can't do anything just with masses, I needed to convert it into moles. So a couple of mole steps. Moles is mass over RFM, or atomic masses. 2.04 over the RFM aluminium oxide, wee bit adding up, ends up being 102 if you add up 2 aluminiums and 3 oxygens. That gives you a number of moles of 0.02. Same for water, 1.08. The mass of the water, or the RFM of water, is 18, which gives you 0.006. Again, some of you will see this straight away. It's 2 to 6 ratio, which is 1 to 3, or again just divide by the smaller one, which is 0.02. So dividing both by that number, you end up with a 1 to 3 ratio. Therefore, the value for N, this missing number of waters, for every 1 aluminium oxide there are 3 H2Os, therefore N is 3.